Lenz's law states that the reaction field opposes the change in the flux that created it. Hopefully you were here and you were not hearing that for the first time on the recording. I'm not going through. Well, I will end up explaining that again, but example. I have an upward initial original field. I have a loop of wire which is going around like my arms. There is a flux through this area. Which direction is the flux pointing? Well, flux is actually technically just a number, but I think of the direction of the flux as the direction of the field, right? I would call this an up flux, okay? Because the field is pointing up. Now I'm going to make the field stronger. I turn up the electromagnet, making the original field. Which direction is the increase in field? I have an up field getting stronger, so which direction is the change? The change is up. I'm getting more upness, right? If I have an upward pointing field that is getting stronger, the change is up. So which direction is the reaction field going to go to oppose that? Down. That's it. That's it. That's Lenz's law. Okay, second example. Make sure you understand this. I've got an upward pointing original field that's not going to change. I've got a horizontal loop of wire like this. A horizontal plane of wire like this. Now I'm going to shrink the loop of wire. I'm going to make the loop of wire smaller. Is my flux getting bigger or smaller? Field isn't changing. Area is changing. What is happening to the area? It's getting smaller. What is happening to the flux? It is getting smaller. Which way is the field making the flux? Up, but I'm getting less up field. How do I oppose a decrease in up field? The reaction field is up. Okay? Is good? Making sensey? I'm not going to give you this in the homework exams or quizzes, but I think it's worth talking through right now to see if you understand this. I'm not going to give it to you because calculating numerically with this involves trigonometry, and I'm trying to skin trig to the bone for this class. I take a loop of wire. Its area will not change. I have a magnetic field pointing up. It will not change. I'm going to rotate the loop of wire so that initially it's being pierced by the field, and it's aiming towards being skimmed by the field. What is happening to the flux through the loop? It is decreasing. What direction does the induced field, the reaction field, want to point? If I am losing flux going this way, it wants to point with the original field. You want to point up, partially. Actually, there will be angles involved and it won't point exactly up. Screw that. Wants to reinforce the original field. I'm getting less and less area being pierced by the plane of the loop. One more example. The left side of the classroom, your left, my right, the left side of the classroom has field pointing up. The right side of the classroom, no field, okay? No field over here. Upward pointing field here. I have a loop, field is pointing up. It's constant. I go to a place where there's no field. What is the change? What is the direction of the reaction field? Point, everyone point. I've gone from up field to no field. What direction is the reaction field? Can't be left, right. It's going to be up, down. How do you oppose a loss of up? You go up. The reaction field points up. What if I go from no field into up field? How do I oppose the increase? Down. Good. What if my loop is like this? Now I'm a prima ballerina. What if my loop is like this? Anyone have ideas? What's going to happen if I go like this? This is a trick question. Anyone see the trick? What? What do you think? Magnetic. Go on. Exactly. So what is the flux? Exactly. Magnetic field, not electric. But yes, 100%. Did y'all hear his response? The field is parallel to the area. The field, an upward field, whether it's zero or whether it's non-zero, is skimming the plane of the loop. There are no field vectors pointing through my circle. There is no flux. There is no induced voltage, okay? Yeah? There will be a motional EMF, by the way. I have a conductor. There's a hole in it. Screw that, though. I've got a conductor which is moving through magnetic field. So as it happens, let's see, V, B, the back side of my wire, the back side of my arm will be more positive and the front side of my arm will be more negative. Or suppose I did this, then my right arm would be more positive and my left arm would be more negative. Still, emotional EMF, we'll review that in a minute. But there's no induced total voltage, there's no current flowing through my arms. Around my arms, I should say. Let's do another example. No. How do you feel like this level is? You feel okay with this? The reaction field opposes the change in the original flux. See nods. Good, good. You're light years ahead of last year. Or maybe I'm teaching better. I don't know. We'll see. Okay. So now I need to teach you which direction current flows in the wire to make the reaction field. This is something that last year I did 5 weeks ago, in the first module when we first talked about magnetic field, and then people's memories are probably distant and faint. For problems where I ask you questions about Lenz's law, I'm only going to give you one shape of wire, circles. And that could be a single turn, multiple turns in place, or a spring shape. But in any case, they're going to be circular cross-section, circular winding. And so current can flow counterclockwise or clockwise through it. Okay? Here is the direction of field inside a loop of wire. If current is flowing, if current is flowing counterclockwise, then magnetic field inside will be pointed out of that plane. If current is flowing clockwise, magnetic field on the inner region will be pointing into page. Here's a quick, dirty trick for how to, well, quick and medium clean trick for how to remember it. Form your right hands into an OK sign. Okay? Your thumb is the direction of the field, and your fingers curl in the direction of the current. You see that? My right hand fingers are curling around the direction of the circle. If the current is viewed from this perspective, if the current is clockwise, my thumb points into page, field points into page. Make sure you're using your right hand, okay? What do I have to do to get an out field? If my fingers are curling around the wire, my fingers are the current now, wrapping around the wire in the same direction that the current flows, my thumb points out of the page. Field points out when you're looking at a loop where current is apparently counterclockwise. How does that feel? Is that okay? That's not that hard, right? It's as easy as a thumbs up. Great. So now let's combine the two things. If I move from a region, let's do the first example again. Here's my loop of wire. Here's my loop. And I'm going to strengthen the upward pointing magnetic field. What direction is my reaction field again? Point for me. I want to oppose the increasing up. To oppose the increasing up field, I want a down field. Now show me with your fingers curling, which direction does makes a downward reaction field? Viewed from my face, looking down, clockwise. Which direction is current flowing through my hand here? If current is going clockwise, viewed from above, point. Which direction is current flowing in my hand? Is it flowing this way or that way? To your right or to your left? Everyone I could see is showing that in my hand, the clockwise current that I look down at and see clockwise circulating is pointing to your left. Yeah, did you get that? Really? Really? If you are lost for the love of dog and all that is unholy, ask me a question. Please. No, I never get good responses when I just say that. Turn to your neighbor and express these laws, and then ask me a question, okay? You got 2 minutes to discuss. Go over it with each other. What? What is going to be done? In the example that I just gave, the applied field, the original field was up and getting stronger. To oppose an up.
Then from that, you can lose.
The current in my loop, to make a down field, show me your right hand, that makes a field going down. Your thumb is the field. Yeah, now curl your fingers. Okay, those fingers wrapping around a loop go in this sense, right? From my perspective, looking down, that's clockwise. So which sense, left or right, does that current going clockwise around? Does that, in my hands, is that leftward or rightward? Your left, yeah, my right, yeah. Good, good. What if, follow-up example, what if I have an upward original field? This is the plane of my loop, and I shrink the loop. Can you reason about which direction the current would be? Tell me why. Perfect, perfectly explained, correct answer. I think you got it. Good, 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 good. David. The magnitude of the reaction of the voltage is the change in flux over the change in time. How much field you get results from how much resistance there is in the coil of wire feeling it, and how much magnetic field that coil of wire generates. Okay. That results in different things. You could tell how much voltage is induced in the coil. You could tell which direction that voltage pushes current. You can't tell the total magnitude of field. That ends up being a really gross equation. You don't want to go there. Yeah. Yes. Area. The area that that flux is piercing, yeah.
So wire point and it's creating this the flux around it, correct? Or is it magnetic field?
Well, I say flux through.
So it's going around the loop this way?
What is going around the loop? Of the original field or the reaction field? Okay, so the original field, I would just say the original field is pointing up in these examples that I was giving. The original field is pointing up. That is a flux pointing, I imagine lots of little lines, little javelins or whatever piercing up through this plane. I'm holding lots of upward pointing spears. There's a positive flux.
Positive flux, negative reaction field.
If it's a negative reaction field, if the original flux is getting stronger.
So if it's staying the same, it's not.
Correct. If you have a constant flux, no reaction.
Flux effect.
No, flux is actually a scalar, but flux results from a vector field. So I abuse the terminology and talk about an upward downward flux. A flux from an upward field, if that flux is getting bigger, the reaction is opposes the original B. If that flux is getting smaller, you want to help the original B.
Explain when tilting, I know it's the flux is no longer going, it's pointing, so you're getting a cosine. And that is doing what?
So I imagine, again, lots of field vectors like a bunch of spears pointing up from the ground or whatever. If I'm holding my hands like this, there are a lot of spears pointing up at my circle. If I turn my arms like this, fewer of those spears, some of those are outside, some of those spears are no longer pointing through my circle. because my circle is getting a smaller shadow, if you will.
So
on the
you have
ground.
more going through it, but less going through a thinner.
There's a less cross section, which for those upward directions would be piercing.
Less.
Less flux in the reaction would reinforce that lost flux.
Okay.
Good. Okay, question me. Let's have group questions. David. Flux is symbolized with the letter phi, a circle with a vertical line. And you could put horizontal bars on the top and bottom if you want to be pretty and make it a capital phi. Other questions? Really? I think that this is the hardest single concept this year. It's a 5-step process if you spell it out. Yeah, please. What do you mean in and out? Wait. On this graph? On this? So this is field is coming out. Field is going in. Properly, flux is a scalar, is just a number. But I'm abusing it. When I say the direction of the flux, what I really should be saying is the direction of the field making the flux is out. The direction of the field which is making the flux is in. Let me test you. Suppose this field gets stronger. The flux is getting more out of the page. Which direction would the reaction current be? Tell me why. No, current can't go in. Current has to go clockwise or counterclockwise. Current in the circle generates a field which will go in or out. You're right that the reaction field goes in. Now, which way do I have to circulate current to get an inward field? That's right. Wait, hold on. I have to remember which direction clocks go. No, a clockwise current generates an outward. Counterclockwise. This is counterclockwise, right? Yeah. Counterclockwise generates an outfield. Clockwise generates an infield. If I want an infield, I need counterclockwise. So the goof that I saw, the only goof that I saw in what you just said was the direction of current that makes which direction of field. Hold up your right hand for me. Careful. Point your thumb in the direction you want the reaction field to go. If this is the plane of the page, your thumb needs to point towards the whiteboard. Okay, away from you towards your computer screen. Sure. Now, are your fingers curling around that clockwise or counterclockwise? From this perspective, this is the direction a clock goes. Okay. Look at the if you are looking at the computer screen, your thumb is pointing away from you, right? Look at the back of your hand. Look at the back of your fingers. On top, when your fingers are above your thumb, they're pointing to the right. When your fingers are to the right of your thumb, they're pointing down. When your fingers below your thumb, they're pointing up. When your fingers are, oh, I can't bend my arm that much. What direction is it when I am pointing, curling around that sense? Is that the way a clock goes or against? The reaction would go counterclockwise if the applied is getting stronger clockwise. Yeah, really? You want more examples? Feel free to ask a follow-up. Let's go to David, though. This is the outward direction, yeah. Yeah. Out of page towards viewer. Out of page is into face. Out of face is into page. This is out of page. Other questions? Give me more questions. Give me more questions. It's the hardest thing this year. You must have questions. Please. Up and down with what? Be precise. Yes. If your field is up, currents are circulating this way or this way. That's harder for me to describe in a horizontal plane. What I would have to say is, all right, current is going, I don't know, this way. Viewed from above, I'm looking down, that's clockwise from above. But if you look at a clock from the other side, counterclockwise from above, clockwise from above is counterclockwise from below, so you have to be precise. I'm looking down on something curling this way, that is clockwise from above. Clockwise from above, what direction a current would make clockwise from above? Good, that's right. More questions? No. Hey, one more follow-up, by the way. This is something I didn't tell the 3 o'clocks, but we're right there. We're right there. This last question just gave rise to, well, second last question just gave rise to this. The example I just gave here, just now, just right now, suppose we've got a clockwise current, the counterclockwise current. If this counterclockwise current gets stronger, what happens? Counterclockwise current gets stronger, generates more out-of-page field. More out-of-page field makes a reaction field point into page, right? Which direction does the reaction voltage want to push a reaction current? Clockwise, in the opposite direction of the original current change. Yes, I started with a counterclockwise current getting stronger. My reaction opposes the increase in current strength. What I'm talking about here, what I will test you on, is if you got one loop of wire going clockwise and counterclockwise and getting stronger, that will induce a clockwise reaction. The fascinating science of it is, though, that this original current will also feel a push. This original current will feel pushed against. If you try to strengthen a counterclockwise current, that clockwise push will slow the rise of the current which made it. Normally, you can't push, you can't exert a force on yourself, but I'm telling you that if I try to make this current stronger, the effect of the magnetic field will be to actually slow the rate it gets stronger. This is called self-induction, and it is beyond what I'm going to test you on. But it's so wild that a current can push on itself, can oppose its own change, and I will hint for the ham radio nerds in this class that this is actually important for ham radio. We'll talk about this outside of class. This is a real effect. This is actually part of technology. David. What change? Be precise. The thing is, you can't beat the original. You'll never beat the original applied field. So if this current is getting stronger, the reaction to that tries to oppose its increase. It won't overcome the original. Is good? Yeah? More examples. Yeah? Right? You need more examples. Question me first. Please. The magnitude of the field is a complicated calculation. You don't want to go there. What I will ask you is the magnitude of the voltage, the magnitude of the current that is fighting or helping. You don't know the formula. I haven't taught the formula that tells how much the magnetic field a given amount of current generates inside the wire. It's not terribly complicated, but I don't remember there. This is a step too far. So you want to find the total amount of actual field, that's beyond the scope of what I'm teaching. Ask me after class. Okay, more examples though, more examples. I want everyone to be solid on this. Everyone who is still showing up to class at this level, I want you all to be golden. So for your classmates who skipped school today, are going to be desperate for help, you could charge them $100 an hour tutoring. Okay, so what do you want to change? Let's have a rightward magnetic field. and a loop which is going okay. So I have a rightward magnetic field, and I've got loops of wire. Watch carefully, look carefully. The loops of wire are going, I've got a resistor, wire goes up, and then it loops around and around, around and around, and down this way again. Okay? Can you visualize that sense of wiring? It's hard to see in a perspective diagram, yeah? Yeah? Viewed from this side, the wire is coiling around this direction. Viewed from the left, it's coiling clockwise. Okay? So the front side of the wire then goes down and back. Okay. My challenge to you is to say, suppose the coil of wire, suppose the magnetic field gets stronger. I'm going to apply more rightward field. Your task, work with your neighbors, Google question A, which direction will current flow in this resistor? You can reason through this, you could do any problem I give you. Okay? Again, the sense of this wiring. No, I described the sense of the wiring wrong. I described the sense of the wiring wrong. I go to the right, and then I come back down. This wire is behind that wire. Let me shade the wire so that the side closer to you is bigger. There. You see that? Can you visualize the sense of it? Do you guys know what Necker cubes are? When looking at a perspective diagram, look. Which side of the cube is towards you? Is this face towards you? You can imagine that this face is towards you. That face is towards you, or is that face towards you? You can't tell just by looking at a wireframe. So I have to specify. This is called a Necker cube. It's an illusion to illustrate the futility of wireframe drawings. But if you imagine this side of the loop is there, so this wire is coming down behind the right-hand wire going to the resistor is coming down behind the plane of the loop. Is good? Yeah. It flips. It flips. Well, no. The magnetic field that I drew is the original field. There's going to be a reaction field due to the loop, but I haven't drawn the loop that makes this field. Now, to answer that question, to make that field, I would want a wire loop that loops this way, clockwise from our perspective.
So electricity is going from the right hand side and spiraling backwards, but it's still making a field to the right.
Whether the current is flowing like this or like this is immaterial. The important thing is whether current is flowing like this or like this. So it doesn't actually matter which. It's whether it's clockwise or counterclockwise, not the slow drift of current along or against the solenoid. Field B gets big. Yeah, I'll write it down. Through the resistor is right or left, baby. Cannot be clockwise, counterclockwise. I'm asking about the current in the resistor. Olivia, yep. Nope. I will oppose the change. 16 correct answers, 17 correct answers, 18, 19, South by Southwest. Zwanzig, 21, 22, 23. Oh my God, you got it. Left. Okay, here's how to do it. Here's how to do it. Pay attention, step through with me, and tell me. I'm going to show you how I get the answer. And once I go through this, I want you to tell me where you dropped off, okay? So first, how I reason through this. Applied field is further right. Reaction field opposes the increase in right field. I want a left field. Did you get this far? No. Okay. If I've got rightward and getting stronger, which is the change? Is the change more right or more left? The response to the more right is left. Okay. The change, if I've got a right field getting righter, the change is rightness. The reaction to rightness is leftness. Turn to your neighbor and express why. Okay, real fast. I oppose the change. The question is, which way does current flow in the wire, in the resistor, which you can only figure out if you can reason about which direction does current have to flow in the secondary to make a reaction field point left. It's a multi-step process. You can't just say one thing, one step. Hold on. Yes. Yes. You don't need to know which one overpowers. You just need to know if this sucker is generating the leftward field, then the current in this has to be going this sense to make it make a left field. Don't think about the original. Once you know that the reaction field is leftward, you don't need to think about the original field at all. Correct. The original field doesn't push the electrons. Okay, give me questions about that first step. Rightward, stronger, reaction is left. Please. The reaction field results from current in this solenoid, this loop of wire, and that is what's pushing the electrons around in here. Does that make sense? Does that answer your question? No, you don't like that. Say it again. Ask me again. Maybe I'm answering a different question. Does the original field push the electrons? Is that your question? The original magnetic field itself does not push electrons in that resistor, does not push electrons in that loop. That's a good question. How can you prove that the original field doesn't push on charges? Okay, so in the beginning, if there is no current in that right-hand wire, the magnetic force law, QVB, is 0. There's a magnetic field, but there's no velocity in here. So the magnetic force doesn't push things this way, that way, or the other way. Furthermore, once current starts to flow in this loop, which direction is the force on that current? The force on that current doesn't push it around the wire at all. The magnetic force would be, let's see, I'm imagining a positive charge there. V, B, that force would push the positive charges inward concentrically. Magnetic force would push the right-hand rule. Magnetic force would push positive charges towards the inside of the spiral and negative charges towards the outside of the spiral. Magnetic force, use the right-hand rule, does not push around the spiral. It is not a magnetic force that is moving this current. It is an electric force. And the electric field is a new phenomenon. It is a new subject from yester class. Ampere's law says that electric fields can also be created not just from charges, but also from changing magnetic fields. Yeah? It's good? Other questions? Correct. The original magnetic field does not exert the force that drives this current. It is the electric field which springs into existence as a result of this. It is a different law of physics. David first then.
Say reaction field, kind of like the opposite of how we would describe acceleration.
Sure. Sure.
We also say that the reaction field is electric.
The reaction field is a magnetic field, I promise, a real magnetic field. Because the reaction field is created from the electricity flowing in the second wire. That electricity is driven by a voltage in the second wire. That voltage does correspond to an electric field, but the electric field that pushes charges around in this wire is different for the magnetic field, which is pointing through the wire. The electric field is actually a circling electric field. The magnetic field is actually a straight magnetic field. So there are both electric and magnetic fields which result from this. The changing magnetic field itself creates an electric field spiraling. That electric field spiraling drives a current, which creates a magnetic field. Two facts, two fields. Last questions. No, I didn't finish walking through this to ask you where I'm dropping you. Okay, so a stronger right field, reaction magnetic field left. Y'all now good with that? Yeah, good. No, not up, left, hey. Okay, so a leftward field, if I hold my thumb leftward, that says the current is spiraling through this wire. Viewed from my perspective, the current is spiraling counterclockwise. Now, if I look at this perspective drawing, which direction is a counterclockwise current going to come out of the system? Left or right side? Loop. Comes out of the far end and then flows leftward through the resistor. Can you visualize that in this spring? Yeah? Last chance for questions before I move on to a different example. Hey, give me a thumbs up, this is, I feel like I'm getting this. This is, I'm more confused than at the start. And you can give me any angle between to say, I may or may not be getting this. Yeah, I kind of get this. I'm really nervous. Oh my God, no one is straight down. All right, I'll take it. I'll take it. Good. More examples. Now let's go through the slide examples. I close the switch. What direction is the current in the resistor? For the sake of this diagram, I want to point out that this wire goes up from the bottom. This wire goes up from the bottom. This wire comes down from behind, okay? Work with your neighbors. This will be question B in the Joule form. Direction of current in the resistor when I turn on the battery. Ah, it should be louder in here. This is hard. You need each other. Help each other. It's dangerous to go alone. Take each other. Which direction is current flow in the resistor when I turn the switch on? Left or right? Probably not that bad. If you want to learn how to calculate the total magnetic field in these cases, I can teach you. I'm not going to subject the whole class to it, but there's some neat stuff there. You can learn this. What? Force of what? Yes, always, in general.
So, and I mean, this is like an opposite, this is like a reactionary mechanism. So
But fields are not forces.
it's kind of what I'm, so I'm wondering, like, I mean, I know it's not like that, but I'm just saying, you know, I guess like what's causing it in reality, and then why does it have the tendency to be?
So ultimately, physics can't answer the question of why is reality like this. Physics can describe what reality is like. And this is, at the end, if you push me hard enough, what I'm going to be forced up against my back is to say that I am describing what we observe in reality. I can't say why reality picked to be this way. But I can't relate this back to things that you're used to. Magnetic and electric fields independently have, you've experienced magnetism, right? You've seen a compass, you've played with bar magnets before, you've felt static electricity and stuff, you have intuition about these, but this is not a force that this is not a connection that you've experienced directly. You just don't have an intuition about this stuff. Nor are there any other fields that I can think of that experience this relationship as between electricity and magnetism.
I said they're not, like, they're reactionary will never be greater than the original, or like
Think.
always 3/4.
It depends on the situation. You can have almost complete cancellation. You can have cancellation which is really slow. It depends on how you build the solenoids, how much resistance there is here, there, and everywhere. Yes, you can predict it to excellent precision. You just need a few more calculations than what I've given you, a few more equations. No, there's technology that depends on this. This is known, this is calculatable to exquisite precision, and the experiment and the theory match up exactly. This isn't as mysterious as it may perhaps sound. Um, if there is a mystery, it's because I have to hand wave whenever I'm describing things that are really geometric calculus. Because it's an algebra-based class, the mathematics to do a lot of these calculations are just not the scope of this class. I can't prove these things with algebra. All right, let's see who got the answer right on the Google form. Actually, I don't know the answer. I will figure out the answer as follows. Ready? Here we go. I turn on this battery. That makes current flow away from the positive end of the battery, out this, and loop around this way, and this way, and this way. I hold up my right hand. That makes a field pointing leftward. Hey, same as, no, opposite the previous, okay? A leftward oriented field coming into existence, the reaction field points rightward. How do I make a rightward field? A rightward field, the spiraling of the current around goes like this with the direction of my fingers. Okay, if the wire is carrying current down in front, that carries current down and points to the right through the resistor. If you got rightward, that is the correct answer. And let's see, let's count how many people got this. Well, let me reassure you, this is as hard as it gets. Not many people got it right. Okay, but let me ask you, where did you drop off? Did you correctly conclude? Give me a show of hands and hold them high so I can actually count here. How many people got that this current creates a leftward pointing initial field? Okay, so the vast majority of you are comfortable. And when the original field is left, which direction is the reaction field point? Who got that the reaction field points right? Okay. To make a rightward field, which sense does the current have to flow? From my perspective, to make a rightward pointing field away from me in this perspective, viewing from the left side of the diagram, that's clockwise. Who got that the sense of the current is this way? Raise your hand high. Okay, and let me just check, if you're not just not voting, who didn't get that the sense of the current is this way? Half of you aren't voting. You either got or didn't get it. Come on, let me see your hands. Who got that the sense of the current is this way? For realsies. Okay, so that's where we're dropping off. That's where we're dropping off. That the direction of the current that makes a field going rightward. Yeah, please ask. What goes to the left? Be precise. Current in this wire goes left. Yes. Yes. The current going left comes out of this wire and enters the coils wrapping around this way. Ah, very good. Yes, that has screwed up a bunch of people. Very good. Okay. Everyone, did you hear that confusion? This is maybe a very common goof. Your classmate asked, the current wraps around the solenoid and the current is going rightward. Why doesn't the field point right? There is absolutely a rightward trend to the current. However, the fact that the current is going around and then around and then around and then around this one, the gradual rightward drift is insignificant compared to the fact that the current is going aroundward direction. Theoretically, there is a component of the magnetic field pointing upward, I think, as well. I'd have to sit down with a piece of paper to work it out. There is a fact that there is a current drifting to the right, but the slow motion to the right as we go from this winding to this winding to this winding is much, much smaller than the fact that all of the current is flowing this way, through this wire, then that wire, and this wire, all the way around. So the short answer to your question is ignore the motion of the current from one loop to the next and just look at the aroundward direction of each loop is this way or that way. That's the major component of the field. Yeah? Good question. Yes, please. In the battery, you betcha. the current in this wire flows counterclockwise from our side of the diagram. If current leaves the positive side of the battery, it's going up this wire, and then which direction does this wire come? This comes out of the page this way. This sense, viewed from your and my perspective, is counterclockwise. David. Yeah. That's what he said. Yeah.
Wire opens the switch at the beginning. It went behind the rod instead. It was
Flip it. I'd flip it completely. Yep, good. Brandon.
The other side for the reaction field, you just kind of look at it and be like that, so if they were flipped, the directions on the other side, we just look at that and be like, okay, it goes.
Yeah, you look at viewed from the end, clockwise versus counterclockwise, not left to right, right to left. Not in the wire up here. You don't care about that. More follow-up questions. Okay, let me give you, before we are out of time, I would like to review the core of Ampere's law, because last class, I remember what I'm seeing now is you just answered a whole bunch of questions at the beginning of this class, answered a whole bunch of questions correctly about is there flux, is there not flux, am I changing flux, which way am I changing the field that makes the flux? But I want to make sure that you are able to calculate voltages correctly. And there's one subtlety that I didn't go into before about number of turns. So to review from last class, yesterday class we learned that voltage is induced whenever flux in a region changes. I do want to be precise and admit it's not the fault of the wire that there's a voltage. The voltage, just like if you have a charge, there's a voltage around it, irrespective of whether, and perhaps even irregardless of whether there is another charge to feel that voltage. Even if there's no wire, there's still a voltage present in the air. If there is a wire, that voltage may drive a current, which drives a reaction field, which blah, 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 blah. But, when a magnetic flux changes in a region, there will be a voltage, an electric field even, present in the air surrounding it. I'm going to remind you the definition of flux is field times area, and to be precise, if you're taking the MCAT, field times area, magnetic field times area times cosine of the angle between them. Field, for the non-trigonometric people, field times area piercing the field. This is a flux. This is not a flux. No flux. Flux. The field has to be perpendicular, or at least partially, perpendicular to the area. If the field is skimming the area, no flux. Another fact I did not tell you before, you will see this in the homework system, you can guess. WB is not just a television network, it is also the unit of flux. The SI unit for flux, a Tesla meter squared. Tesla meter squared is a Weber. Weber. It's a fun sounding unit. The WB is a Weber. And again, here is the fundamental foundational law called Faraday's law. To find the voltage induced, we could find the rate at which flux changes, the slope of the flux versus time. Webers per second tells you the voltage induced. What happens if I don't have one wire but two? Will the first wire feel this voltage? Yes. Will the second wire feel this voltage? Suppose I have two loops of wire. Will the first wire feel that voltage? Yes. Will the second wire feel that voltage? What if, instead of two isolated loops, I have them connected like a spring? This turn of wire feels that voltage. This turn of wire feels that voltage. How much total voltage is felt when you have two wires in series? Twice as much voltage. Voltages in series add up, yeah? Okay, so your textbook, I hate this, your textbook writes this law as n times the rate of change of flux. No! There is voltage present in the space around the magnetic field which is changing to the tune of delta phi delta t. If you have multiple turns of wire, each turn feels that voltage. Voltages in series add up. So if you're doing a homework problem where you have 5,000 turns of wire surround some changing flux, your total voltage across the total, all 5,000 turns, is 5,000 times this number. I strongly encourage you to think of that in 2 steps. N delta phi delta t hides the fact, makes you think that there has to be an N turn coil of wire. This voltage is present in the air, and if you taste that voltage N times, multiply out, okay? Do you smell what I'm stepping in? See the distinction I'm making here? The number of turns in the wire is what your textbook defines. Capital N, number of turns in a loop surrounding this region. Do you see what I'm going for? Yeah. I hate it. Multiple textbooks, not just our textbook. Multiple textbooks write N delta phi over delta T. No N! The voltage exists in space delta phi delta T. If I feel it multiple times, that's due to the coil. Okay. So now, what affects V? What affects V? You have to change your flux. If flux don't change, if there is no change in flux, there will be no induced voltage. Delta phi is 0, V is 0, right? Look at that equation. The numerator is 0, you have no V. Now, how do I change phi? I change phi by changing B or changing area. If B changes, if the magnetic field, the applied original magnetic field changes, B changes, phi changes, I've got a V. If area changes, phi changes, I've got a V. I want to emphasize, by the way, a couple of things here. Area, it's not just important that I've got, you know, a loop of wire that's getting smaller or a loop of wire that's getting bigger, a rectangle that one side is sliding further out. What's important is where the field is piercing that area, okay? So suppose I've got a constant loop of wire. Let's imagine that everywhere the light strikes on this screen is magnetic field. I've got a constant loop of wire. The loop is in the magnetic field, in the magnetic field, in the magnetic field, leaving the magnetic field, out of the magnetic field. The loop never changed its radius. The loop never changed its area. Nevertheless, that fraction of the loop that was in the magnetic field absolutely changed. This is a changing flux. It's not just the area of the wire, it's the area that field is present in. Ultimately, B times A is not about the wire surrounding it, it's about the region of space that B is piercing. Okay. Question? Correct. Yes. Good. Other question? Now, MCAT students, wait, I have a bunch of MCAT students, right? MCAT students, we will also ask, they will also ask, they may ask, not always on. We don't deal with trig in here much. I'm going to avoid it whenever possible. I'm not going to ask you about this, but MCAT may. If you turn the loop of wire, you intersect more or less field. Look at my circle, look at my shadow, for instance. My shadow right now. There's a lot of light piercing the plane of my loop. What happens as I turn? My shadow is smaller. There's less and less light piercing my loop. When I'm edge on to the projector, there's no light passing through my circle, all right? I'm looking at it edge on. Then there's more and more. There's a change in flux if you rotate a coil of wire in a field. In fact, that's where the electricity that generates these lights come from. Palo Verde Nuclear Power Plant makes its electricity by rotating a loop of wire around a permanent magnet. Bang! That's where the electricity comes from. Yeah. Nope. Flux is a measure of a field, and the field itself is not mass moving. That field can push mass, can generate kinetic energy, but the field itself is not motion. I described going a lot of set times. That's no. Good. Which? The total field is the sum of the original two fields, the original and the reaction. We only actually see the total. You can't tell cause from effect. But if you want to calculate it, if you want to think about it, you got to distinguish clearly. The real master field is the sum of the individuals.
So that does not mean it's not allowed.
Well, it's possible in some circumstances. If you have a superconductor, there can be no magnetic field inside a superconductor because currents in a superconductor flow with zero resistance, and you can have infinite, nigh infinite current in a superconductor that will always flow to cancel out magnetic fields inside. It's called the Meissner effect. You can look it up. So it's possible to have complete cancellation, but 99.9% of the time, no, you won't. It'll offset the magnetic field, but you won't cancel completely. Magnetic field is not a thing with mass. It cannot itself be pushed upon. But you can affect the magnetic field in a region by creating another magnetic field. Yeah. Okay, almost done, almost done, almost done. Which is good because we're almost out of time, almost out of time, almost out of time. Point 4 here. I've talked about how to change B changes phi, A changes phi, angle changes phi. Change in phi is not V. V is change in phi divided by change in time. So induced voltage is inversely proportional to the rate at which voltage changes. If I take twice as long to change the phi a given amount, the voltage will be halved. Conversely, if I shake a magnet near a loop of wire faster, the faster I shake it, the less time it takes to change that flux, the bigger the induced voltage will be. In fact, this is how we generate really honking big voltages at power plants. You spin a loop of wire frickin' fast around a permanent magnet. Those turbines are going like cray-cray. What doesn't induce a voltage? Suppose I am a loop of wire. Here's a magnetic field coming this direction. If I move this direction, I am encountering the same field vectors, the same field lines, piercing through me just as much. No change in flux. There might be a flux, but it's not changing, no voltage. Okay, so moving along a field line. Do you guys know the word translating in this context? Translating, moving straight along a field line, no change in flux. Also, if I move a coil and a magnet next to each other in the same direction, there is no induced voltage. The magnetic field is moving along with the coil of wire. You are not changing the field in the vicinity of the wire. The wire feels a constant voltage, constant flux, no voltage. So far, so good. All these points easy peasy after what we saw before. When a bar magnet moves towards a coil, bar magnets, as you've probably found, when you hold two bar magnets closer together, they pull on each other harder. Magnetic field is bigger near a bar magnet. Closer you get. So if I move a bar magnet towards a coil of wire, magnetic field goes up, flux goes up, induced a voltage. The faster I move it, oh, I just said this, the faster I move it, the voltage is bigger because I'm decreasing the rate, increasing the rate, decreasing the downstairs, delta phi over delta t. If t gets smaller, V gets bigger. Hey, think about this. Multiple turns of wire. If I double the number of turns, what happens to the amount of voltage? Double. If I double the number of turns, what do you think happens to the total current in the coil? Trick question, nothing. Why? I've increased the voltage, haven't I? V equals I times R. If I'm just talking about the resistance of the wire, if there is no separate resistor like in those earlier problems, just the wire itself, the length of the wire doubling, the number of turns in the coil doubling, increases the resistance as well proportionally. So if I've just got a loop of wire, doubling the number of turns does double the voltage, but it also doubles the resistance, so current stays the same. Don't memorize current always stays the same. If I've got, 500 turns of wire, I don't know, 10 ohms, making this up. If that 10 ohms of wire is also connected to a 1,000 ohm external resistor, the total resistance isn't doubled when I double the coils. I've gone from 10 ohms wire resistance to 20 ohms wire resistance. The total resistance doesn't change, right? Don't just memorize doubling turns doesn't double current. Think about it. If I double the turns of the wire and there's some other external resistor, not just the wire resistance, the total resistance might not even significantly change. Then the current would double. Do you see what I'm stepping in? Smell what I'm stepping in here? Yeah? No? Yes? Okay, I'm seeing people nodding along, whether that's, oh God, there's only 3 more minutes. Oh God, there's only 3 more minutes or not. Let's find out. We already did this. One more time. I want to end the class the way we started it. Let's restate Lenz's law. We know how to calculate Ampere's law, the magnitude of induced voltage. V equals IR lets us calculate magnitude of induced current. But that's as far as I'll ask you for magnitudes. Directions of current comes from Lenz. The induced current's magnetic field, what I've been calling reaction field, opposes the change in the original flux that induced it. So, to solve these Lenz problems, find the direction of the original field, find how that field is changing, oppose the change, build up weakening fluxes, oppose strengthening fluxes, and then finally use the right-hand rule. I'm only ever going to give you coils that react to these. Use the right-hand rule to figure out one this way, that way, the other way. Clockwise, counterclockwise, which direction does that push current? How do you feel about this? Give me what's the last question? What are we up to? D in the Google form? Question D. C. Oh God, did not do enough. Question C, out of 5, how do you feel? 1, more confused about Lenz than before I knew what Lenz was. 5, I am bored. We should have done this faster. 3, I'm not confident, but I think I get it. 2, I'm definitely confused. 4, yeah, this is good, but we needed the whole period. Yeah? You see my ranking scale? Okay, well, I'm getting 3s and 4s and a couple 5s, and an occasional 2. I'll take it. Congratulations, y'all. This is the end of electricity. Almost the end of electricity. We've just got a little bit alternating current. I'm going to keep that fluffy. We're basically at the end of the module. I love each and every one of you. Get out of here. I have answers.